Good afternoon, Southminster scholars. Welcome back. In continuing our exploration of the solar system, today we're going to talk about the space age solar system. The space age, which began October the 4th, 1957, when Sputnik 1 was launched, that transformed our view of the entire solar system. Computers and digital technology created new and faster ways to observe, to analyze the sky. Satellite missions gave astronomers greater details than ever before. We began to, and continue today, to gain ever-increasing knowledge of our solar system. Today, Dr. Summers will introduce and detail how our evolving technological advances results in greater knowledge of the universe. When Dr. Summers concludes his lecture today, stay tuned for an unusual edition.
October 4th, 1957. This was the beep heard round the world. The Soviet Union had launched Sputnik 1, an 84-pound satellite, just a 23-inch sphere, but it orbited Earth every 98 minutes for 22 days. The beeping could be heard by amateur radio operators, and it spread the immediate message that the space age had begun. For astronomy, no other event in history changed our view of the solar system like the ability to explore it. It is not a coincidence that NASA was founded almost a year to the day after Sputnik 1 launched. Considering the magnitude of the knowledge explosion that happens during the space age, it's helpful to explore what we knew at the dawn of the space age and take a look at the technological advances that would enable a plethora of new discoveries. By the mid-1900s, our model of the solar system was well established. There was the Sun, the 9 planets, remember Pluto was still a planet back then, their moons, some asteroids, and some comets. And most folks' idea of the solar system was one of the orbits of the planets around the Sun. I have an interactive 3D program here that I can use to illustrate this idea. We start by looking at the orbits of the inner planets, the rocky planets, Mercury, Venus, Earth, and Mars, and you can see that they are ellipses, or nearly circular ellipses around the Sun. The rocky planets are in close, but if I back away, you can begin to see the outer planets and Pluto, Jupiter, Saturn, Uranus, and Neptune. And you can see that Pluto's orbit looks like it crosses Neptune's orbit, but that's really just a projection effect. It's a highly inclined orbit, and if I put things edge on, you can see that the 4 giant planets lie mostly in a plane, while Pluto lies distinctly out of that plane. If I wiggle it back and forth just a little, you can see that Pluto's orbit doesn't really cross Neptune's orbit. It is totally distinct from Neptune's orbit. Let's go back into the inner planets, and you can see that they too lie in a plane. So all of the planets basically lie in the same plane as Earth's orbit. If we go back to the face-on view and turn on time, you can see that Mercury orbits much faster than Venus, which orbits faster than Earth, which orbits faster than Mars. This is the Keplerian motion that comes from the universal law of gravitation. As we go out, you can see the same thing is true for Jupiter. Let me turn on time a little faster here. Jupiter moves faster than Saturn, moves faster than Uranus, moves faster than Neptune, and slowest of all is Pluto. The planet's orbit in timescales of a few months for Mercury up to a few centuries for Pluto. Now, what that interactive couldn't show you was the size scale of these objects. And the size scale of the solar system is really vast. It's almost too vast to be comprehensible. So I like to shrink the solar system down to a manageable size scale in order to understand it. My favorite comparison is, what if the sun were the size of a basketball? Standard basketball is 9 inches across. Well then, what would be the sizes of the planets? Jupiter would be a sphere about 1 inch in diameter. Saturn would be about 3/4 an inch, or 2 centimeters. Uranus and Neptune are both about 1/3 of an inch across, or a little less than a centimeter. Earth is very small, and it's only 2 millimeters in size. Actually, I had to put it inside some pieces of tape, otherwise I'd lose it, because it's so small. That is the true size of our planet compared to a basketball sun. It's really only about the size of these little nibs, these tacky nibs to give you a grip on the basketball. Venus is about the same size as Earth, again, 2 millimeters in size. Once you get smaller than that, I couldn't find any spheres to fit things. So, for Mars, I found a large paper clip. And if you hold it up edge on, that's about the size of Mars. Mars is only 1 millimeter in diameter in this scale model. Mercury, well, that's about the size of a small paperclip, a normal paperclip. It's less than 1 millimeter in size. And finally, Pluto. Pluto is so small that the only thing I could find was a piece of pencil lead 1/2 millimeter in diameter. That's really small. So that's it. That's the scale of the solar system. You have a basketball sun, we've got a 1-inch Jupiter, all the way down to a 1/2 millimeter size Pluto. From this, you can easily see that the sun contains 99.86% of all the mass in the solar system. Basically, you can forget all this stuff. This is just flotsam and jetsam. This is really the whole solar system. Now, the natural question asked here is, how far away would I have to put these planets in order for them to be at the right distances? In order to get enough space, I would have to use a football field. Here is a diagram of this basketball sun-based solar system laid out on a football field. If the sun is on the goal line, then our millimeter-sized Mercury is out at the 21-yard line. Venus is out at the 39-yard line. Earth is across midfield at the opponent's 46-yard line. And Mars is all the way 80 yards away on the opponent's 20-yard line. These tiny millimeter-sized objects are spread out across the length of a football field. When you go out to the outer solar system, then you're going much further away, and our 1-inch Jupiter is more than 2.5 football fields away. 3/4-inch Saturn, 5 football fields away. Uranus is a bit less than 1 kilometer, and Neptune is a little less than 1 mile. Pluto, which is only 1/2 millimeter in diameter, is over 2 kilometers away from this basketball-sized sun. So you have to try to imagine that. For 4 kilometers across, there is just one basketball, a couple big-sized marbles, a couple small marbles, some really tiny BBs, and then a bunch of really small things, and even smaller than that. And then there are the asteroids and comets, which they're just flotsam and jetsam. They don't even add up to a good small moon. The solar system is really mostly empty space. It's really kind of amazing. It's kind of amazing that we've actually been able to traverse it. With space age, we were able to extend across the solar system. How did we do that? Well, with a lot of technology. The technology has really brought about a revolution in our ability to observe and understand the solar system. Some of this technology allowed us to build telescopes in other wavelengths of light. You see, we see visible light, but visible light is just a tiny fraction of the full electromagnetic spectrum. Visible light is depicted here in the middle of the electromagnetic spectrum, and it has a small range in the middle, but extending on to very long wavelengths, we have radio light, microwave light, and infrared light. And going to shorter wavelengths, we have ultraviolet light, X-ray light, and gamma ray light. Light is really just the same phenomenon, whether it's gamma ray light or radio light. It just has different wavelengths. And that's what this wave is supposed to depict here in the middle of the diagram. The wavelengths for gamma ray go all the way down to 10 to the minus 13th of a centimeter, whereas wavelengths for radio light go on up to a kilometer or larger. So it spans a huge range. And visible light is just about a factor of 2, a very small region right in here in the center of that. When we use telescopes in these other wavelengths, we see a lot more of the universe. For example, when we look at Venus in visible light, it's rather bland. It's kind of boring because it's entirely cloud covered, and it really just reflects most of its light back to space in the visible. But if you use ultraviolet light, you're able to see through those clouds and actually start to see structure in the atmosphere of Venus. This image here, I know has to be in ultraviolet light because I can see the cloud structure in the atmosphere of Venus. If we look at the sun in visible light, it looks, again, like Venus, it looks a little bit bland. It's basically a nice smooth sphere, and maybe it has a few dots on it, the sunspots on it. These don't look terribly impressive. However, when you look at it in X-ray light, the sun comes alive. Those sunspots are areas of fierce magnetic storms and are emitting huge amounts of energy in ultraviolet and X-ray light. By studying all the different wavelengths of light, it gives astronomers a more complete picture of the physical processes taking place in our universe. Another major technology that has helped astronomy is digital technology, computers. When we used photographs for astronomy, they were an analog medium. The emulsions of a photograph respond in a complex way to the amount of light that is absorbed. Because when a photograph absorbs twice as many photons of light, it's not necessarily going to be twice as bright. And as astronomers, we need to know how much light had been absorbed from an object in order to understand it. So we had to measure what we call the response curve of a photographic emulsion. When we move to digital images, we bypass that and we're able to get a quantified numerical measure of the light received. We use something called CCDs. It stands for charge coupled devices. These are the same things that are in your digital camera. You might even have a digital camera on your phone these days. Well, astronomers have been using CCDs for about 20 years, and they were actually an important secondary market for the makers of CCDs, so astronomers in a way helped bring about the camera that you may have in your phone today. And once our data has been recorded digitally, we have it available for computer processing. And that can bring out details that are impossible to extract from a photograph. Now, for example, this is an image of a nebula, and it is done at a low stretch so that we can see the details in the very bright regions in the center of it. If instead I computer processed it to bring out the faint details, while the central region will be overblown, but I could see the details in the outer region, you see how much nebula there really is. We can then work with it to try and come up with a balanced stretch digitally and come up with an image like this. We can also take multiple images of it and digitally combine them together so that we can get a color composite of various wavelengths, looking at it in different filters, red, blue, and green, also filters that respond to different hydrogen atoms or calcium atoms or helium atoms. And you can get a wonderful color picture like this. Using computers also opens up ideas for using simulations. We have supercomputers that can process data very quickly, and we can take ideas that we could never observe in nature and simulate them on a computer. For example, there are two images of a galaxy collision sequence. In the top image, you see the two galaxies before they've collided. They're trapped in each other's gravity, and they're about to smash through one another. The bottom image shows the computer simulation after the two galaxies have collided. This simulation was run on a supercomputer about a decade ago and took about a week's worth of calculation time. In nature, the process would have taken about 1 billion years, but we can simulate it on the computer and study it. Now, I know this is a course in the solar system, and these galaxies aren't part of the solar system, but trust me when I say we use computer simulation all the time in solar system objects as well, specifically for calculating orbits and observing the stability of the orbits within the solar system. Computers are also very useful in working with our telescopes. A computer-controlled telescope are easier to operate, they can be larger, and they can be more accurate. Matter of fact, professional astronomers never move a telescope anymore. For one, there are telescope operators on the mountain, and number two, even the telescope operators don't move those big telescopes anymore because they're all controlled by computers. And sometimes you don't even have to go to the mountain. Sometimes you can actually control the computer over the internet, and you don't even have to leave your research institution. As an example of telescopes that are heavily controlled by computers, let's look at the twin Keck telescopes. Here they are on the summit of Mauna Kea in Hawaii. The Keck telescopes are 10-meter reflecting telescopes, but 10 meters is larger than the largest piece of glass we can make for a mirror. How do they do that? Well, the Keck telescopes are actually a segmented mirror. In this image, you can see the mirror stretching 10 meters across, and I've overlaid these hexagons to show you the segments of the mirror. There are actually 36 hexagonal segments that build up this entire mirror. Behind each mirror, there are sensors and actuators, and twice a second, computers line up the edges between those segments. The edges have to be lined up to a very precise amount because you have to get down below the wavelength of light. They are lined up to 4 nanometers twice a second. Without computers, the Keck telescope would be impossible. You can also use computers to link together telescopes, and this is very common in radio observations. Here we have a radio telescope array, and each of these dishes is a radio telescope in itself. But all of the radio telescopes in this long array are linked together by computers, and all of their observations are brought into the central computer and correlated together, and by combining the signals from all of them, you effectively get one radio dish as large as the entire array. What's even more impressive is that you could take an array here in the United States, an array in Europe, an array in Australia, all around the world, and tie them together, and you effectively get a radio telescope as large as Earth. This is being done, and it's called Very Long Baseline Interferometry. And they provide radio telescope observations that are the highest resolution that we can get. As good as that is, it still helps to get off our planet and above our atmosphere. Because Earth's atmosphere actually blocks most of the light reaching it. As we can see in this diagram here, the visible light is transmitted through Earth's atmosphere, and radio waves mostly get through Earth's atmosphere. Infrared light can be seen pretty well from mountaintops, but most of the rest of the radiation doesn't get through our atmosphere. Most of it absorbed either high in the atmosphere or about halfway down through the atmosphere. Now, this may sound strange because we use sunblock to protect us from the UV radiation of the sun. Not that much UV radiation is truly getting through. If the complete amount of UV radiation were truly getting through, we'd need some really serious sunblock. The other thing Earth's atmosphere does is, of course, it distorts the light that does come through. The observations we make from telescopes on the ground are a little bit blurry because of the motions within Earth's atmosphere, and we can really only see resolutions down to about 1 arc second on most telescopes on the ground. So getting above Earth's atmosphere will enable us to see wavelengths that we can't see from the ground, and it will also give us better observations in the wavelengths we can see. The most famous satellite telescope is the Hubble Space Telescope. Here it is shown in its orbit above the Earth. It is about 360 miles above Earth, and if you look on this image, you can see along the Earth's atmosphere. The atmosphere is only about 60 miles high. So Hubble skims along just above Earth's atmosphere. We say that it's in low Earth orbit. I often describe Hubble as having a bird's eye view because it's up high and it has very fine resolution. Hubble, not being limited by Earth's atmosphere, has a resolution down as fine as 1/20th of an arc second. This gives it the finest resolution in visible light of any telescope. And most of the spectacular nature of the images from Hubble comes from this vantage point in space. Now, this is low Earth orbit. In contrast, the Spitzer Space Telescope is much farther away. Instead of being hundreds of miles from Earth, it is tens of millions of miles from Earth. It's actually farther from Earth than the Moon. Spitzer is an infrared telescope, which you may know is associated with heat radiation. And it is advantageous for Spitzer to be out at that distance so that it gets away from the heat of Earth. Hubble and Spitzer are just two of NASA's great observatories. The other two are the Compton Gamma Ray Observatory that observes in gamma rays, that's already completed its mission, and the Chandra X-ray Observatory that observes in X-rays. These are a suite of observatories placed in space to do general observing in 4 major wavelength bands. But we have also sent a fleet of other more specialized observatories to look at the universe in many, many different wavelengths. In this chart, we show many of the space missions that have been launched and the wavelength coverage that they've got. We can see we have several missions out here in gamma rays, many in X-rays, some in UV, visible, all through the infrared, microwave, and we even have some radio telescopes in space. These missions allow us to see the universe in new ways and in finer detail than we could from the ground. Finally, beyond just looking at the universe, in the space age, we have gone there. We have taken the next step and become explorers of our solar system. We have manned and satellite missions that have gone across the solar system and uncovered details that enrich and have transformed our scientific views. The most famous of these is, of course, the Apollo missions to the Moon. These Apollo missions transformed the Moon into a real place and transformed humanity into adventurers across the universe. Here's one of the most famous images. This is Buzz Aldrin and the American flag on the Moon, and it evokes sort of patriotic sense that we have conquered, well, I don't think anyone thinks we've really conquered the Moon, but at least we have conquered the way to get to the Moon. As an astronomer, there are 2 things I notice about this. Well, 3 things actually. First is that the flag is being held up. All right, that waving in the flag, that's not real. Because the second thing I know about this is there's no atmosphere on the Moon. If you look beyond the horizon, it's pitch dark. The third thing I notice about it is all these footprints down here. And if you think about it, there is no atmosphere, there is no rain, there is no erosion on the Moon, and those footprints are still there. Those footprints will be there for billions of years. Another thing, as an astronomer, that I like about the Apollo missions to the Moon It's not necessarily the pictures of the astronauts, but they're the pictures of the moon itself. This image of a crater taken from the Apollo orbiter somehow speaks to me. It really brings up a visceral sense of the moon. And you've got this giant crater and all these small craters around it. And I immediately start imagining the impact events that must have formed this surface. To me, the close-up images that we have of the moon and all the other planets from our space missions have taken these places and put them into my mind, have provoked my imagination about what the universe is really like. They give me, I don't know, texture to the solar system. But even before we went to the moon, we started visiting other planets. This image here is a drawing of the first interplanetary probe, Mariner 2. It was launched August 27, 1962, on a mission to Venus. It was followed by many other missions. There were the Venera probes to Venus, which, by the way, landed on its surface and then promptly melted because the temperatures on Venus are so hot. There are the Mariner missions to Mercury, the Vikings missions to Mars, Galileo to Jupiter, Cassini to Saturn. We even have the New Horizons mission going out to Pluto, and it'll get there around 2015. There are two missions in particular that struck me as I was growing up. The first one are the Voyager missions to the outer solar system. Shown here in this diagram are the plots of the Voyager missions. Voyager 1 went past Jupiter in 79 and Saturn in 80, and then continued on out of the solar system. Voyager 2 followed shortly thereafter and continued on to visit Uranus in 1986 and Neptune in 1989. They took some amazing pictures of these planets. They discovered moons and rings, and they transformed our ideas about the outer solar system. It really ignited my imagination. And what's really nice about these Voyager missions is that they're still going. They have exited the inner part of the solar system, and now they're about 100 AU away from the sun, and they're on what they call the Voyager Interstellar mission. In a few years, they're going to reach the edge of the solar wind and explore the heliopause. These two small satellites, launched in the late 1970s, are still going 30 years later. The other missions that really excited my imagination have been this fleet of Mars missions, starting with Viking in the 70s and extending on through the several missions we have at Mars today. We have orbited, we have landed, and we have explored the red planet. This image here is one of the best images of Mars that we can get from Earth. It's an image taken by the Hubble Space Telescope, and it's fantastic for an Earth-based image. But if you really want something cool, well, we've been there. This is a famous image called Twin Peaks, referring to the two peaks in the background. And basically, it looks like a rock garden on Mars. It was taken by one of the rovers, and the rovers have moved throughout the landscape and examined the geology and searched for water. But more powerful is the infusion of this as a place into my imagination. We have transformed those tiny spots of light that I've seen through telescopes and made them into known worlds. We have begun to explore our neighborhood in space, and it has become part of our thinking. When historians write the history of the solar system, they tend to focus on the Copernican revolution. It's often cited as, the biggest change in our view of the solar system. We went from the Earth-centered to the sun-centered. As an astronomer, I have to disagree. I think that the space age is the more important epoch. The space age brought us new ways to observe the solar system in more wavelengths and with bigger telescopes, new ways to analyze with better data and faster processing, and also a new way to explore, both with robots and with our own eyes, we have gone through the breadth of the solar system. This image here, very famous image, Earthrise, symbolizes the change in perspective. When we as humans see our own planet rising and we see it in space as it truly is, we no longer think of the system as out there. It has become real, up here. It has become part of our mental model, and we see our place in the solar system anew. The capabilities enabled by the space age have changed our perspective more than anything else in history. And in the next several lectures, we will explore in detail the range of observations, ideas, and discoveries enabled by the space age. Until then, have a wonderful day.
Most of these eerie things are absolutely impossible on our planet, even in the wildest imagination. But as practice shows, what is impossible with us is still possible on other planets. Let's look at ordinary rain as an example. Rain is usually cold and gloomy, and very, very wet. And in general, the Earth's rain, well, it's boring. The rain of stones on planet Korat 7b, however, is quite another matter. We wouldn't be bored there. It's very, very hot on one half of this strange space object. The surface temperature reaches 4,700 degrees Fahrenheit. That's about 2,600 degrees Celsius. And that's more than enough to make the rocks melt and then evaporate like puddles of water here on Earth. At the same time, the other half of the planet is relatively cool at about 3,500 degrees Fahrenheit. That's about 1,900 degrees Celsius. So, the rocks evaporate and then condense into huge stone clouds under the hellish temperatures on the hot half of the planet. And then these clouds fall as rains of magma heading back to the surface. On the relatively cooler side of the planet, the rain made of magma solidifies into stones before hitting the surface. This is real stone rain. Can you imagine seeing this with your own eyes? But wait, this next place will astonish you even more. HD 189773b is an exoplanet located 63 light-years from us. It's slightly larger than Jupiter in size, and most likely you will agree with me if I say that it looks awesome. Can you possibly imagine what horror lies behind all this beauty? Its fantastic appearance is due to the fact that the atmosphere of the planet consists mainly of silicate particles. Think sand or glass. It also rains at a temperature of 1,700 degrees Fahrenheit. That's 930 degrees Celsius. And it has winds that often reach 5,400 miles per hour. That's 8,700 kilometers per hour, which is 7 times faster than the speed of sound. This is even more terrifying than the rains on the previous planet. Here, they're as clean as glass. Just imagine the scene. Clouds are coming from behind the horizon. Echoes of thunder crack through. The wind surges to a speed of 1.24 miles per second. And finally, the sky explodes with pouring rain. Masses of glass are tearing through the atmosphere and into you at insane speeds. If such a storm suddenly arose on Earth at the same wind speed, it would fly around our planet at the equator in just 5 hours and 33 minutes. Local residents would feel it quite powerfully. But speaking of winds, really, this is nothing. This puny little storm is just a breeze compared to the wind that blows on planet HD 189733b. The temperature on the solar-facing side of the gas giant often reaches a mind-boggling 1,770 degrees Fahrenheit, and the temperature on the dark side is usually no lower than 1,270 degrees Fahrenheit, or about 700 degrees Celsius. The small temperature difference between the two sides is due to the extremely fast winds, which here reach a fantastic 21,747 miles per hour, which is 6 miles or 10 kilometers per second, almost 29 times faster than the speed of sound. That's some wind. As I said in one of my past videos, the fastest wind ever recorded on Earth was during a tornado in Oklahoma in 1999, and its speed reached just 300 miles per hour, which is 73 times less than the usual average breeze on HD 189733b. If you had wings, or a parachute, or even just a normal umbrella, you could fly around the entire planet in about an hour and 8 minutes just by opening that umbrella. But something tells me that your body would probably suffer some terrible indignities long before that. Stones falling from the sky, 5,400-degree temperature, glass rain faster than the speed of sound. You know, the more I learn about this, the less I have doubts about the existence of hell. I left off early the last episode on the topic of shadows. So let's continue. Let's imagine that there's a place where the rays from 2 suns wake you up in the morning. You could also watch 2 or even 3 sunsets at almost the same time in the evening. Previously, it seemed like a fantasy and was possible only in Star Wars, until we discovered the amazing Kepler-16b exoplanet, which orbits in a system of 2 stars in the Cygnus constellation. 2 suns rise and set on the horizon of this planet. And if my shadow was suffering the despair of loneliness here on Earth, then on Kepler-16b it would have a friend. Although, most likely, if I could somehow teleport to this planet, then in a moment I would certainly die from the heat and lack of air. But if you allow me the luxury of a super-duper spacesuit, and I somehow stayed alive, in general, 2 suns and 2 shadows is certainly cool, but not as cool as 3 suns and 3 shadows. Astronomers have discovered an even more amazing object, HD 13199ab, relatively recently. This new planet broke all previous records. It revolves around 3 suns at once. It also has a giant mass, 4 times larger than Jupiter's, and an unusually long orbit. A 1-year revolution of the exoplanet around its 3 stars takes 550 of our terrestrial years. And as the planet spins quite slowly, the 3 suns only descend from the sky in about half of this time. Imagine that you wouldn't see a single sunset for 275 years. This all happens 340 light years from our Earth, which is 300 light years further than our next exhibit, the planet ocean Gliese 1214b. You all know that water occupies 70% of the surface of our planet, but in our case, it's only 0.005% of the total mass of our planet. Scientists believe that on our distant neighbor, water could be up to 10% of the total mass of the whole planet. This means that Gliese 1214b is completely covered by a huge ocean reaching hundreds of kilometers in depth. The planet is 2.5 times the Earth's radius and approximately 6.5 times larger by mass. If you look at all those creations that live in our Earth's oceans, which is less than 6.8 miles in depth, it's scary even to imagine what monsters could hide in this terrible place. But most likely these monsters exist there only in my imagination. In fact, the bottom of this huge ocean is under such incredible pressures that life there is, in principle, impossible. It's known only that the water at the bottom of this mega ocean could likely be an exotic form of ice, known as Ice 7. However, all my searches for information regarding this strange substance were unsuccessful. I still don't understand what the reality of this ice really is, in addition to the fact that it doesn't look like ice in the usual, normal, earthly sense, as it is apparently not cold at all, but is still solid in form. If you have a broader knowledge regarding this topic, please tell me about it in the comments. And for dessert, the last planet. A real hell here, my friends. Many stars can't even boast of the same high temperature of which the planet Kelt 9b is burning. Approximately every 1.5 days, this planet, the size of our Jupiter, makes a complete revolution around its star. This star at the moment is one of the biggest stars near which scientists have managed to find planets. The A-class blue giant star Kelt 9, whose age is estimated at about 300 million years, is approximately twice as large and twice as hot as our Sun. Because of its giant size, the planet Kelt 9b, which rotates in the immediate vicinity of this super hot reactor of a star, is heated to an incredible temperature of 7,800 degrees Fahrenheit, a about 4,300 degrees Celsius. This is fantastically hot, as it's within spitting distance of the temperature of the surface of our own sun at 9,900 degrees Fahrenheit. Most stars of the spectral classes F, G, K, and M do not exceed 1,300 degrees Fahrenheit, and only representatives of classes B and O get above 18,000. Thus, the exoplanet discovered by Scott Gaudy with the help of a pair of Kelt telescopes turns out to be hotter than many stars. I don't know about you, but I just can't get this amazing fact out of my head. But this is not the end. They dress up in eccentric suits with wings, climb to some very high point, the tip of a steep rock on some mountaintop is just about right, and they jump. I don't know what these kamikazes are thinking, flying at insane speeds just a few meters from the protruding rocks and trees, but it looks simply just plain terrifying. Then the parachute opens. The adrenaline surge peaks, and with unforgettable emotions, his feet finally find firm ground underneath. And yet, the most incredible feeling of all was when he defeated the old man with the scythe, Death himself. They say you really begin to appreciate life only moments from death. This is called base jumping here on Earth, one of the most extreme and dangerous sports. I don't know about you, but in my eyes, these crazy daredevils with wings look like superheroes. But you know what's even more fun? There's a place where all this devilry would look like no more than an innocuous walk in the park. This place is right here in our solar system, 71 light minutes from Earth, 9.3 billion miles from our blue-green ball. If some daredevil wanted to repeat such a jump on Titan, he could make it all the way around this picturesque moon of Saturn. A dense atmosphere combined with low gravity makes this place a superb candidate for the resettlement of Homo sapiens in the future. Just imagine what mind-blowing entertainment could be invented under such fantastic conditions. I would finally be able to realize my most cherished dream, to ascend into the air like a bird and soar. As you already know, it's not only birds that can fly. We just have to figure out how to get to Titan, and also how to make a cozy little nest there. And this, believe me, will not be easy. The fact is that in addition to all these bonuses awaiting future colonists, Titan has prepared for us a good little bundle of troubles. But this place is quite impressive. There's an atmosphere here. Moreover, it's 1.5 times denser than our terrestrial one, and this is about as good as it gets. The force of gravity is 1/7 that of the Earth. Yes, Titan is even smaller than our moon. This means that a person could potentially just walk around on the surface of Titan in nothing more than some simple scuba gear, which is also very, very not bad. But now comes the pain. First, it's terribly chilly. The temperature of the Titan atmosphere is minus 290 degrees Fahrenheit. This is in addition to the fact that the average wind speed reaches as much as 20 miles per second. This means that walking on the surface can really only be possible in the vicinity of a powerful heating installation, probably with a nuclear or a thermonuclear reactor. Also, this super dense atmosphere does not contain precious oxygen, but contains such very cheerful substances as cyanogen and cyanic acid. This means that the atmosphere is not just unfit for breathing, but is poisonous and at the first opportunity will try to kill you. Consequently, all shelters on Titan should be completely hermetically sealed, and at the entrances and exits must have airlocks that do a complete and thorough replacement of the air. Since this is a world full of hydrocarbons, but with an oxygen deficit, which would be needed to burn the hydrocarbons, energy and transport on Titan will be arranged quite differently from that here on Earth. The substance acetylene, which decomposes with the release of heat, is at the bottom of Titan's lakes. It could be used as fuel, as an analog for coal and gasoline. Neither solar nor hydro energy will be much of an option. Hydropower won't be so effective as the rivers on Titan move very slowly. Wind power might be a good option, but beyond that, uranium will be needed for nuclear reactors for heating for settlers. And unfortunately, it's lacking on both Titan and in the Saturnian system as a whole. There are practically no heavy elements and metals, so most likely they will have to be delivered from asteroids. The best transport solution is airplanes, helicopters, and airships, considering the dense atmosphere and very low gravity. By the way, an inhabited base filled with oxygen at a pressure of 1 atmosphere may well be lighter than titanium air, so that it could become similar to an airship. Imagine how cool it would be to live in such a flying city. Since there's no global ocean, rivers and lakes periodically dry out, so water transport is immediately thrown into the background, although with special need it could be used from time to time. If you use acetylene as a fuel, wheeled vehicles are also possible, but there will be a variety of problems with this, including wet sand, rough terrain, and of course, the wind. Therefore, it will be more expedient to use railways with trains on magnetic cushions for cargo transportation. My space broadcast comes to an end for today. Thank you for watching,